The Phoenix system will be the primary armament for the Navy's F-111B, the A version of which is shown here in an early test. Phoenix is comprised of an airborne missile control system, AMCS, 6 guided missiles and their launchers, and special support equipment for both the AMCS and the missile. This system will detect targets at ranges greater than 80 nautical miles and will display the tracks of as many as 18 targets simultaneously. Moreover, it will have the firepower to attack 6 targets at the same time. These targets can be at ranges out to 55 nautical miles, altitudes from sea level to 80,000 feet, and traveling at speeds of up to Mach 3. During 1964, the Phoenix system design was approved by the Navy, and its major elements were converted into operating hardware: the AMCS and its support equipment, the missile, its special support equipment, subsystems, special components. Finally, preparations for the flight test program were begun. The film that follows briefly describes these accomplishments. In 1964, the AMCS progressed from breadboard to flight-quality hardware. Here, for example, is the radar transmitter breadboard, as it existed early in the year. And here is the first flight package transmitter. Pressurized and liquid-cooled, it features a single high-powered traveling wave tube. We have made similar progress in all other areas of the AMCS. To date, we have built and tested some 80 traveling wave power amplifier tubes. In so doing, we're incrementally meeting all performance specifications. Tubes for which the design was concentrated on bandwidth have achieved the required bandwidth of 750 megacycles. Tubes designed for gain have demonstrated the required 50 dB of gain. Tubes designed for power have produced the required 3 kilowatts of average power. We are also nearing the required efficiency and are confident we can build a tube with 50 dB gain at 3 kilowatts, operating efficiently over a 750 megacycle band. At the end of this report period, the first model of the Phoenix computer was being tested by the subcontractor, Litton Industries. This computer will process target data and perform the missile control computations. Here is the interface unit, which converts the input signals into computer language and converts the computer outputs into usable form for the rest of the AMCS. The arithmetic and control unit does the actual computations. This is one of the 2 non-destructive readout memories. It contains core storage for 8,000 24-bit words. The first model of the controls and displays subsystem was also in test at Litton. This panel configuration stems from the combined design efforts of 5 Navy agencies, Hughes and Litton. This display shows the missile control operator, the tactical situation. This detailed data display shows him the radar and infrared outputs. While the hardware was being fabricated at Litton, control and display simulation studies were proceeding at Hughes in order that the human engineering portions of the development program could proceed on schedule. Hughes proceeded with work on the computer programs. The track while scan program was coded and punched on tape, checked on an IBM 7094 computer, and is now ready for loading and checkout on the Phoenix computer. A prime achievement of the year was activation of the roof house test facility for the AMCS. It went on the line on schedule with the delivery of the power supplies in August. During the latter part of the year, every bit of the first system hardware was installed and operating, except for the computer and controls and displays. Here is the radar transmitter. Its successful operation has verified its design. The receiver's narrow-band parametric amplifier is electronically tunable over a wide band and has a 3 dB noise figure, features never before achieved in an operationally packaged airborne system. The Doppler filter bank has 768 crystal filters. These are 1/2 the size of filters previously available for airborne Doppler processors. The range processor is essentially a special-purpose device that extracts the range information developed in the Doppler signals by the 3-slope modulation of the transmitted signal. The single target tracker provides a conventional tracking mode in which a target Doppler signal is velocity tracked and target position, derived from silent lobing information, is used to position the antenna on target. The planar array antenna has been operated over its entire 750 megacycle RF bandwidth and has very nearly met the specified gain of 37.5 dB over the band. It is positioned by a self-contained 1500 psi hydraulic system. Also operational in the roof house is the IR search track set. The IR detector employs 8 highly sensitive indium antimonide elements. They are mounted in a vertical array to provide 2 degrees of elevation coverage with 2 milliradian azimuth coverage, yielding a resolution of 1 milliradian in azimuth and 5 milliradians in elevation. The Missile Auxiliaries subsystem, which had been behind schedule, was delivered to the roof house in November and integrated with the system. This subsystem serves as the interface between the AMCS and the missile. The first experimental model of the special support equipment has also been installed in the roof house. It is being used here not only to check out the system, but to further its own development. In August, the mock-up of the operational version of the special support equipment was inspected and approved on schedule by the Navy. At the close of the year, the equipment in the roof house was being checked out unit by unit with the aid of the experimental special support equipment. If Lytton delivers the computer and controls and displays as now promised early in 1965, we should meet our next major incentive milestone, the roof house system demonstration, on schedule. Progress on the development of the Phoenix missile and launcher in 1964 is best exemplified by this complete brass board of the missile electronics. Accepted by the Navy in August, the brass board functionally integrates the complete Phoenix missile guidance system, an integration which otherwise would not have occurred until the first flight-quality missiles were assembled. This brass board will enable us to work out our integration problems early in the program and to design the special support equipment concurrently with the missile. The following are some of the highlights of missile and launcher development during the period. All elements of the missile guidance system are in an advanced stage of development. The seeker head, which mounts and positions the antenna, has been verified in simulated operational tests. It also passed the required vibration, shock, and thermal tests. Here we demonstrated stabilized mode of operation, which holds the antenna on target during launch transients. The receiver transmitter, which provides semi-active mid-course and active terminal guidance, has completed more than 500 hours of test. The klystron used in the receiver transmitter was developed by Hughes. Under exhaustive tests, it has exceeded both stability and power specifications. The fabrication of a flight-quality receiver transmitter using this tube and packaged to the missile configuration is well underway. The electronics unit, which derives the missile guidance signals, has likewise operated successfully in the brass board. The difficult problems of packaging and cooling this unit in a compact flight configuration have largely been solved, and we have started fabrication of the flight quality unit. The final element of the guidance unit, the radome, is also on schedule. Here is one of 14 different radomes of identical external configurations, but varying wall thicknesses, which we are evaluating. Results of this evaluation will lead to selection of the optimum design. The firing of 17 heavyweight case motors by Rocketdyne has verified the basic motor propellant composition and grain configuration. Simulated high-altitude test firings have shown that radar attenuation caused by the plume will not prevent the transmission of command signals from the missile control system to the missile. Lightweight case motor firings, which began in October, have demonstrated that internal insulation is adequate and that the required impulse can be achieved. The 3-section battery is undergoing developmental tests by Delco Remy on schedule. The electrical conversion unit has operated successfully in the brass board, and operational units are now being fabricated for on-schedule delivery. The first hydraulic power supply unit was delivered by the subcontractor Pesco Products. It is shown here with its special test equipment. Autopilot components are being readied for system testing. Shown here are the prototype components of the adaptive roll system. The 4 servo positioners, which operate the missile control surfaces, are being fabricated. Here, the attitude sensor for the autopilot is being tested. During the year, the missile underwent over 500 hours of wind tunnel tests. Supersonic and transonic tests of the aerodynamic configuration determined fuselage stability, control characteristics, and panel loads. Structural tests of the missile began in the fall of 1964. Shown here is a static load test of the wing on the rocket motor section. This is a static load test of the X-1 separation test missile on the launcher. The X-1 missile was accepted by the Navy. It will be used for flight separation tests from the A-3A aircraft early in 1965. The mock-up of the shipboard operational support equipment for the missile was approved by the Navy in August, and the recommendations of the mock-up board are being implemented. The shipboard support equipment will provide go, no-go performance testing, fault isolation to a single missile section, and 5-minute checkout time. The first experimental model of the missile special support equipment was accepted by the Navy in September. It is now being used to determine the inputs and outputs required for shipboard equipment. It is also being used for development testing of the missile. The second model of this equipment, completed in early December, is awaiting Navy acceptance. In January 1964, a mock-up of the Universal Launcher was demonstrated for the Navy. The demonstration included loading and unloading the missile, and loading and unloading a bomb. Subsequently, we built and tested a gas ejection system for the launcher. In July, ejection tests with the T-3 structural test missile began. To date, more than 100 tests have been performed. Here is a low-temperature icing ejection test. In December, 3 additional launchers were completed and accepted by the Navy. 1 will be used for ground testing and the other 2 for flight tests on the A-3A aircraft. At Navy's request, Hughes prepared a proposal for an integrated pylon launcher. It would reduce the weight of the weapon system by 300 to 400 pounds. In April of 1964, the first two A-3A aircraft were delivered to Hughes for service as Phoenix test beds. The aircraft are being modified for the Phoenix installation. The nose compartment is being extended 40 inches to accommodate the radar. A bulkhead is being installed on which to mount the radar antenna and an F-111B radome. Two missile launchers are being installed on pylons and added to the fuselage. The flight test program will get underway in January 1965 as scheduled. As you have seen, 1964 was a year marked by steady accomplishment. Highlighted by two successful program reviews, it saw the Phoenix design approved and converted to operating hardware. Since its inception 2 years ago, the Phoenix development program has been on schedule. 1965 will see the first separation missile launch and the start of flight testing of the complete missile system. 1966 will see the first guided missile launch from the A-3A and the installation of the complete missile system in an F-111B. The Phoenix guided missile system is being developed for the Navy's F-111B by the Hughes Aircraft Company. The system consists of the AIM-54 missile, the missile launchers, and the AWG-9 airborne missile control system, plus their special support equipment. This film presents the technical highlights of the Phoenix development program, January through December 1966. In 1965, flight tests of the Airborne Missile Control System, AMCS, were initiated in the A-3A aircraft. Both IR detection and radar detection in the range rate mode exceeded specifications. During 1966, in a continuation of AMCS flight tests, the radar detected A-3A targets at ranges up to 115 nautical miles and tracked single targets at ranges up to 80 nautical miles. In tests of the infrared subsystem, F-4 targets in nose approaches were detected at ranges up to 102 miles and tracked at ranges up to 58 miles. Back in October 1965, captive flight tests with the G-2 missile were initiated. Since that time, G-2 has logged over 65 hours in the air. G-2's captive flights paved the way for the successful Phoenix guided flights in 1966. On 12 May, under control of the Naval Missile Center, Point Mugu, Phoenix Missile G-4 was launched in the program's first guided flight, 1 month ahead of schedule. The missile operated in its home-on jamming mode. The target was Orion Firebee BQM-34A, equipped with an electronic jammer. Target range at launch was about 22 miles. The missile scored a direct hit. A few weeks before this test, in April, the first F-111B assigned to the Phoenix program landed at the Hughes airstrip in Culver City. On 16 August, 30 days ahead of schedule, installation of the Phoenix system in this aircraft was completed. The 36-inch planar array antenna and 3 kW radar transmitter are located in the nose of the aircraft. The Block 2 computer is located in the aft electronics bay behind the cockpit. The radar data processing equipment is located in the same area. The Block 2 controls and displays are installed at the MCO's station beside the pilot. While installation and checkout of the equipment in the F-111B was underway, activity continued in the Phoenix Missile flight test program. On 8 September, the second guided test of the Phoenix Missile took place. The target was a BQM-34A. The test utilized two A3As. One carried the airborne missile control system and continuously illuminated the target in the single target track mode. The other A3A carried the missile. At a range of about 21 miles, the missile was launched. It homed on the pulsed Doppler radar energy returned from the augmented drone. This was the first integrated evaluation of airborne missile control system and missile, and the first use by an air-to-air missile of an adaptive autopilot. The launch was clean and stable. For the terminal part of the missile's guided flight, we switched to the target. Several cameras recorded the missile's close approach with their 160-degree fisheye lenses. This is one view. The action is slowed about 80 times. Here's another view from the target. Reduction of the target camera data indicated that missile G6 passed within 20 feet of the target, well within the specified 25-foot radius. 1 month later, in October, an airborne missile control system was delivered to Grumman, 20 days ahead of schedule. The system is being used in their F-111B Electronics Integration Laboratory. Concurrently, an experimental set of special support equipment was delivered to Grumman. Meanwhile, a quarter-scale mock-up of the fleet-configured special support equipment underwent an initial design review. The design was approved with only minor modifications. Developmental models of the special support equipment are currently being fabricated to the approved configuration. In November, the MAU-84A integrated pylon launcher built by Hughes and General Dynamics underwent a detailed design review by the Navy. A number of modifications were instigated. Incorporation of the changes will be completed in early 1967. Subsequent to the design review, the integrated pylon launcher and missile successfully underwent a vibration test in which inertia and aerodynamic forces were simulated. No problems were encountered. On 2 November, Phoenix Missile X-7 was launched in the first powered flight from the F-111B. The aerodynamic separation conformed to analytical predictions and motor ignition occurred at the proper time. The pylon launcher performed as expected, providing the downward pitch required. Incidentally, the rocket motor completed pre-flight rating tests in August. On 9 December, the 744 bench electrical tests required to verify the airborne missile control system's full range of design parameters were completed. The present system design successfully passed 98% of these tests. Minor modifications are now being incorporated. The final highlight of the year was the accomplishment of track-while scan in flight aboard the F-111B. The operator detected an A3A target over the Pacific Missile Range, and the system tracked the aircraft for 2 minutes while simultaneously searching for new targets. The target was tracked until it passed the F-111B. To sum up, 1966 was a productive year for the Phoenix program. In tests of the AMCS, both radar and IR detection performance not only confirmed analytical predictions, but exceeded specifications. 2 guided flights of the Phoenix missile were successfully carried out. The airborne missile control system completed bench electrical tests. The Phoenix system was integrated with the F-111B. The Phoenix missile was launched in its first powered flight from the F-111B, and airborne track-while scan operation was demonstrated. Looking ahead, extensive flight evaluation of the missile system will continue in 1967. The first test will be a sample data mode launch from the A-3A. It will be followed by the first guided launch from the F-111B. A second F-111B is expected in January. Later in the year, with both F-111Bs in service, an average of 3 missiles will be launched every month. The progress demonstrated during 1966 has yielded a high level of confidence in the readiness of the Phoenix missile system for the transition to pilot production. This phase is expected to be underway in early 1967.
The F-111 tactical fighter, one new aircraft for 2 services, being developed by the United States Air Force. The F-111A for the United States Air Force. The F-111B for the United States Navy. It's a twin-engine Mach 2, 2-place, side-by-side fighter aircraft designed to perform an Air Force tactical mission and a naval fleet air superiority mission. Perhaps the most important feature of the F-111 is its variable wing design. In its extended position, it permits low-speed, short-distance takeoff and landing, and long loiter time. High lift is achieved by the use of slat and flap extensions. With the wings folded back, a near-optimum configuration for high-speed, low-drag, supersonic flight is produced. The F-111 will have approximately 90% mission reliability, a combat ceiling of more than 60,000 feet, sustained speed of approximately Mach 2 at altitude, and a ferry range of approximately 4,000 miles on internal fuel alone. With airborne refueling or external tanks, the range can be greatly extended. Terrain avoidance radar on the F-111A will allow it to fly low-level missions supersonically day or night in all weather. It will land on a sod field over a 50-foot obstacle in less than 3,000 feet. The Navy version, the F-111B, is capable of operating as a combat air patrol on station 150 miles from launch point and can loiter for over 3.5 hours at 35,000 feet. While the 2 aircraft are more than 80% identical, the principal differences between them are in the forward fuselage, fire control systems, the landing gear, and wingtips. Noses of the 2 aircraft differ because of dissimilar requirements. The Navy version is 6 feet shorter and has an upward folding radome for carrier operations. The longer nose of the Air Force version is aerodynamically cleaner for improved supersonic efficiency. Note the ground-level access to all equipment areas to facilitate rapid, efficient maintenance, eliminate the need for work stands, and help make possible a 30-minute turnaround time. In both versions of the F-111, the nose gear has dual wheels and the main gear a single wheel on either side. Both have an emergency free fall capability. The Air Force version has larger tires for operating from sod strips. The Navy model has a wingtip 3.5 feet longer to provide an increased loiter performance over the TAC model. Full use of the variable sweep wing can increase usable wing area by 33%. Electronic equipment is of the module type, which is self-testing. It indicates immediately by a go, no-go signal if it is functioning. If the indication is no-go, a line replaceable unit is exchanged, and a go condition for the aircraft indicates successful repair. Controls, displays, and instrument systems have been made identical wherever possible. In the F-111A cockpit, the pilot station is on the left, and the pilot systems operator is on the right. Each has a complete set of flight controls. The pilot uses mainly these instruments in flight: the horizontal situation indicator, the attitude direction indicator above, and right the vertical speed indicator and altimeter. To the left, the airspeed and Mach indicators. The pilot systems operator instruments are the attack radar in red. Below this, the navigational control panel. To the left are the standby instruments and traffic control equipment. The cockpit interior for both aircraft is similar. However, in the Navy version, there is only one control stick. To the right of the pilot sits the missile control systems operator. The Navy version has automatic navigational and landing capabilities. Side-by-side seating eliminates one complete control panel and the need for a trainer model. Also, it provides much better inter-crew communications and operation. The built-in steps and handholds help a pilot or crewman get aboard or out on the ground without the help of other people or equipment. In an emergency, rocket motors will boost the escape pod clear of the airplane, and parachute deployment will control the descent. The capsule will provide shirt-sleeve environment, safe escape, and recovery throughout the operating envelope of the F-111, as well as at zero speed and underwater. The weapons bay of the Air Force version can carry one special weapon, 2 air-to-air missiles, and numerous combinations of conventional weapons. The Air Force version has 8 external stations which can carry multiple loadings of conventional weapons. In fact, the F-111 will be capable of delivering a complete inventory of the existing special and conventional weapons. Power is provided by 2 fan-type Pratt & Whitney T-30 engines. Right and left engines are interchangeable. This is another feature that helps reduce maintenance time to 35 man-hours of labor for every flight hour. Each engine has a quarter-circle air inlet under the leading edge of the wing, with a self-positioning spike for optimum performance at all speeds. Each air inlet has deflector plates and blow-away jets to prevent foreign object damage during ground operations. Regardless of the differences in the 2 versions, they both emerge from the same airframe. Generally, the differences are only those required or justified by the respective services. Prime contractor for the F-111 program is General Dynamics Fort Worth. The contract is being managed by the Aeronautical Systems Division of the Air Force Systems Command. First flight of the F-111A is scheduled for early 1965. The first Navy flight will follow within a year. Early inventory deployment can be expected following accelerated flight tests.
Aviation, the art of aeronautics, began with the dreamers, inventors, and daredevils who dared to defy gravity. The journey of aviation was nurtured by pioneers like the Wright brothers, whose first flight marked a historic milestone. The role of aircrafts in world wars was groundbreaking, dramatically changing warfare strategies. This initiated a technological evolution in aviation, transforming the simplistic wings of a biplane into the thunderous roar of jet engines. Let's journey through the ages of aviation. Behind every great aircraft, there were great minds. These visionaries, like Sir Frank Whittle, the innovator of the turbojet engine, redefined air travel. Then there's Skunkworks Kelly Johnson, the genius behind the SR-71 Blackbird. His designs combined speed, stealth, and power, crafting machines that dominated the heavens. The contributions of these pioneers have left an indelible mark on the canvas of aviation, shaping the course of history and inspiring generations of engineers and aviators. Each epoch in aviation history gave birth to extraordinary aircrafts, each with their own unique features and roles. The Lockheed SR-71 Blackbird was a marvel of speed and stealth. The F-105 Thunderchief, a supersonic fighter bomber, was vital in the Vietnam War. The P-51 Mustang, a long-range fighter, was critical in World War II. The P-47 Thunderbolt, a heavyweight fighter, was used extensively in the same war. The A-10 Thunderbolt II, the Warthog, is a close air support icon. The Messerschmitt Me-262 marked a leap forward in aviation technology. Each of these game changers were instrumental in their eras, and their legacies still resonate today. Beyond the game changers, there are those that have transcended their practical roles to become icons. The Concorde was not just an aircraft, it was a supersonic symbol of luxury and speed. The B-52 Stratofortress, a strategic bomber, is an icon of power and resilience. These magnificent machines and others like them have become much more than just aircrafts. They are enduring icons that encapsulate the audacious spirit, the relentless innovation, and the boundless ambition that define the world of aviation. For more amazing aerial footage, and to join us in this incredible journey, check out the DroneScapes YouTube channel.
If you enjoyed this video, please remember to like and subscribe. And as always, thank you for watching.